Hello students, welcome to EPG Pathshala. Today we will discuss the 10th module in which we will learn the coagulation-flocculation process as well as the precipitation process. And both of these processes, they are very essential in the water treatment of drinking water as well as the wastewater. First, the coagulation-flocculation, it describes the chemical process of contact and adhesion of the colloidal particles which flock together to form bigger clusters which can easily settle down at the bottom of their own. And the precipitation, it describes the process which occurs during the chemical reaction in which the solid settle down to the bottom of the reaction mixture. We will study the coagulation-flocculation process in which we will study the process of coagulation, the types of coagulants, mechanism of coagulation as well as the coagulation control test to optimize the dosage of the coagulant used in the process. And in the precipitation module, we will study the removal of the metals. We will also study the minimum solubility of the different metals under different pH conditions. We will study the removal of fat, grease and oil, the removal of phosphorus as well as the removal of suspended solids. Let's first start with coagulation-flocculation. The treatment of wastewater is a matter of solid separation since most of the contaminants in the wastewater are present either as the particulate or in the colloidal form. They are transformed into such forms during the treatment. The separation of particulate matter from the liquid phase is one of the important steps in most of the water treatment processes. The water contains both dissolved and suspended particles, and the suspended particles vary considerably depending upon the source. The larger particulate matter can easily be separated using the conventional filtration, sedimentation techniques, while the colloidal particles are difficult to separate from the water as they do not settle by gravity, and due to their small size they can easily pass through the pores of the filtration media. The colloidal particles are very fine particles having the size over a range of 0.1 to 1 nanometer, and they are having electrostatic charge on the surface. So for the removal of these particles, these individual colloidal particles must aggregate and grow in size, and the aggregation of colloidal particles involves the following steps. Number 1, destabilization of the colloidal particles to promote the attachment after they come in contact with each other. And second, the transport of colloidal particles to promote their interparticle collision. The bringing together of the destabilized particles to form the agglomeration is called flocculation, whereas the overall process involving destabilization, transport and floc formation is called coagulation. In general, most of the colloidal material has a negative surface charge, and we know very well that the like charges tend to repel each other, preventing the phenomenon of coagulation. So these characteristics cause the colloidal particles to remain dispersed in the solution. The destabilization of the colloidal particles to promote their coagulation and settlement is achieved by adding the chemicals that coat the colloids by opposite charges. The addition of positively charged ions in the solution will destabilize the colloidal matter and allow their settlement. The measurable quantity which is used to predict the potential of coagulation is zeta potential, and for effective coagulation it is found that zeta potential value ranges between plus minus 0.5 millivolt. Now you can see in this schematic representation that the colloidal particles, they are bearing the negative charge, and the negative charges are neutralized by the oppositely charged coagulating polymer. As a result of this, the colloidal particles agglomerate either due to the charge patch formation or because of the polymer bridging. In the process of water treatment, clarification of the water with coagulating agents has been practiced since ancient times using a variety of substances, and the alum was used as a coagulant in water treatment and more formally in the treatment of public water supplies since 17th century. But in the modern times also, in the water treatment process, coagulation and flocculation are the essential steps. The coagulant chemicals are of two types, primary coagulants and coagulant aids. Let's start with primary coagulants. Primary coagulants are the coagulants that neutralize the electric charge of the particles present in the water. leading the particles to clump together. The chemical coagulation has been in practice for several decades to precipitate the soluble heavy metals which are present in the wastewater as hydroxides, so facilitating their removal by physical separation through the sedimentation. Chemically, the coagulants are either the metallic salts of ferric ions or alum, or it could be the polymers. The process of coagulation consists of the following steps. The first and the initial step is simple addition of the chemical which is used as a coagulant to the wastewater. This is followed by the rapid mixing of the solution to ensure the homogeneous distribution of the coagulant throughout the wastewater. In the third step, the solution is mixed again, but this time at a slow speed to encourage the formation of insoluble solid precipitate, and the process is known as coagulation. And in the fourth, final step, the removal of the coagulated particles takes place by the way of filtration or decantation. Now let's study the mechanism of coagulation. The process of coagulation results from two basic mechanisms, namely electrokinetic and orthokinetic. In the electrokinetic coagulation, the zeta potential is reduced by the ions or colloids of the opposite charge to a level below the van der Waals attractive forces. While in orthokinetic coagulation, the micelles, they aggregate and form clumps which agglomerate the colloidal particles. The addition of high valence cations accompanying the dissolution of the coagulant neutralizes the negative charge present on the colloid before the visible floc formation, and the rapid mixing coat the colloidal particles, resulting in the formation of microflocs. These microflocs then retain a positive charge in the acidic range because of the adsorption of hydrogen ions. These microflocs also serve to further neutralize and coat the colloidal particles, while flocculation agglomerates the colloids with a hydrous oxide floc. In this phase, surface adsorption is also active, so the colloids which are not initially adsorbed are removed by the entrapment in the floc. The commonly used coagulants are metal salts like aluminium coagulants, aluminium sulfate, aluminium chloride, polyaluminium chloride, and sodium aluminate. Iron coagulants includes ferric sulfate, ferrous sulfate, ferric chloride, and other chemicals as hydrated lime and magnesium carbonate also act as the primary coagulant. Alum, the most popular and economical coagulant which is used in the water treatment application. When alum is added to the water, the formation of aluminium hydroxide floc takes place by the reaction between the coagulant and the alkalinity of the water present as hydroxides of calcium and magnesium. If the water to be treated has insufficient alkalinity or buffering capacity, the additional alkali such as hydrated lime, sodium hydroxide or sodium carbonate must be provided for the reaction. The aluminium hydroxide actually exists in the chemical form Al2O3 along with the water of crystallization, and this is amphoteric in nature, means it can act as either acid or base. The alum floc is least soluble at the pH 7. The control of pH is very important in the coagulation process, not only in the removal of turbidity and color, but also to maintain the minimum levels of dissolved residual aluminium in the clarified water. The optimum coagulation pH value should be attained by adding sulfuric acid or similar strong acid rather than the excess of the coagulant. The coagulation process with alum as the coagulant is capable of achieving significant removal of the organic contaminants, but the pH of the water during the process has profound influences on the effectiveness of coagulation. The best results are achieved in slightly acidic conditions. Simultaneously, the optimum pH for alum coagulation is influenced by the concentration of organic matter present in the water. For water of higher organic matter content, the optimum pH is displayed slightly more toward the acidic side. So, the conventional coagulation practice may provide excellent organic removal if the coagulant dose and the pH conditions are adjusted to the optimum range. Iron salts. The iron salts are also the most commonly used coagulant and includes ferric sulfate, ferric chloride and ferrous sulfate. These compounds often produce good coagulation when the conditions are too acidic for use of alum. And the disadvantage of using the iron salts as the coagulant is it becomes more difficult to handle the sludge. Ferric sulfate, this is available in the form of red-brown powder and the formation of ferric hydroxide floc as a result of reaction between the acidic coagulant and the alkalinity of water present as calcium bicarbonate. And similarly, the ferric chloride, which is available as green-black powder and also as a dark brown syrupy liquid, or the crystals of ferric chloride, also forms the hydroxides of ferric ions. And this insoluble hydrous ferric oxide is produced over a pH range of 3 to 13. The floc charge is positive in the acidic range and negative in the basic range. And the mixed charges are there over the pH range of 6.5 to 8. The second type of coagulants are the coagulant aids. Coagulant aid is an inorganic material and is used along with the main coagulant. Coagulant aid, when added, increases the density and provides toughness to the floc so that they will not break up during the mixing and the settling process. The commonly used coagulant aids are bentonite, calcium carbonate, sodium silicate and polyelectrolytes. Polyelectrolytes are high molecular weight polymers that are having the adsorbable groups and form bridges between the particles or the charged flocs. There are three types of polyelectrolytes. The cationic polyelectrolytes, which are adsorbed on negative colloids, anionic polyelectrolytes, which are adsorbed on positive colloids, and non-ionic polyelectrolytes. These polyelectrolytes replaces the ionic group on the colloid and permit the hydrogen bonding between the colloid and the polymer. The quality of the water changes with season and weather. So the coagulant dose have to be adjusted according to the variations in turbidity of the water as well as the organic content. An underdose of the coagulant may cause the sample to appear cloudy with no floc and settling. And the vice versa, overdose of the coagulant may form dense floc that may be fragile and fluffy, which will not settle down when the mixing is turned off. However, the coagulant dose cannot be calculated. They have to be determined experimentally by the jar test, and this test is also called coagulation control test. This test is a simple, effective method that stimulates the coagulation-flocculation process of the proposed water treatment plant. It is widely used laboratory test for coagulation and flocculation control, and the purpose of this jar test is to select the type of coagulant used and its dosage. The coagulant aid which is used, its dosage, determining the optimal pH for coagulation, determining the point of chemical addition, optimization of the mixing time and intensity for rapid and slow mixing. Now let's study this jar test procedure. As you can see in the picture, the jar test procedure involves the following steps. First, the jars has to be filled with the water sample and they are kept on the magnetic stirrer. The coagulant is added to each container in small increments at a pH of 6. After each addition, the contents they are stirred rapidly for 1 minute followed by 3 to 5 minutes slow mixing. The rapid mix stage helps to disperse the coagulant throughout each container, and this mixing is continued until a visible floc is formed. Using this dose, place the 1 liter of the sample in each of the 6 beakers shown in the picture, and the pH is adjusted in each beaker in the range of 4 to 9 with the standard alkali. And this is followed by the rapid mixing of each sample for 3 minutes, followed by gentle mixing for 15 to 20 minutes to allow the flocculation. After that, the effluent concentration of each settled sample is measured. After measuring the turbidity, the percentage removal in terms of turbidity unit is plotted versus pH, and the optimum pH is selected. Using this optimum pH, the coagulant dose is optimized, and the plot between the percentage removal of turbidity versus the coagulant dosage will give the optimum dosage of coagulant used in the process. If the coagulant aid is to be used, the whole procedure is repeated, adding the same towards at the end of a rapid mix. The values that are obtained through the experiment are correlated and adjusted in order to account for the actual treatment system. The another method of separating the suspended and dissolved substances from the water is precipitation, which we will study now. Precipitation, it's a method for the removal of metallic suspended solids, fats, oil and greases, as well as other organic substances from the wastewater that are either dissolved or suspended in the solution. These dissolved or suspended particles can be made to settle out of the solution as a solid precipitate, which can then be easily separated either using sedimentation, filtration or centrifugation. The voluminous precipitate formed can capture the ions and particles, causing the sweeping of these ions and particles from the wastewater. And the process of precipitation can also be assisted through the use of coagulants. The method used for precipitation will depend upon the contaminants to be removed from the wastewater. The different methods were adopted for precipitation and they are described as below. Metal removal. For the removal of the metals from the wastewater, we first study the metal hydroxide solubility curves at different pH. The heavy metals, which are generally precipitated as hydroxides through the addition of lime or caustic soda. The addition of these chemicals change the pH of the water to a pH of minimum solubility of metallic ions present in it, and this value can be taken from the graph. And the pH of minimum solubility, it varies with the metal. When treating industrial wastewater containing the metal ions as the contaminants, the pre-treatment of the wastewater is necessary to remove the substances that may interfere with the precipitation of these metals. Specifically, ammonia and cyanide ions, they interfere with the removal of these metals from the wastewater. These interfering contaminants form the complexes and limit the removal of metals by precipitation. Further, cyanide can be removed by alkaline chlorination or catalytic oxidation, and ammonia can be removed. Once rendered insoluble, these compounds will tend to precipitate and settle. Since the optimal pH for precipitation depends both on the metal to be removed and on the counter ions which are used, hydroxide ions, carbonate ions or sulfide ions, and the best treatment procedure must be determined on case-to-case basis. After the optimum pH for precipitation of various metallic contaminants is established, the settling process can be accelerated by the addition of coagulant, which gather the insoluble metal compound particles into a coarser floc which can settle down rapidly under the influence of gravitational force. For the removal of fats, oil and greases, which are the organic substances having density less than water, and they are floating on the surface forming the surface slicks rather than settling to the bottom of the water. They behave in this way because they are hydrophobic, non-polar substances and insoluble in water. These free-floating slicks can be removed by skimming the surface of the solution. However, the oil, fat and greases can be emulsified in the aqueous solution by the addition of surfactants. The addition of surfactants will disperse the oil and fats into smaller globules which remain suspended in the aqueous solution. And the substances, soaps and detergents, they act as the surfactants. They help in making the hydrophobic substances soluble in water. These dispersed globules can be removed by destabilizing the electric charge attraction that keep the localized globules of oil in solution. This can be done with the addition of a polymer which acts as coagulant and leads to charge neutralization. In this way, the charge attraction of the oily particles is disturbed and it allows them to separate out from the aqueous solution. For the removal of phosphorus from the water, the procedure involves addition of lime or metal salts, and the metal salts commonly used are ferric chloride or aluminium sulfate. And these metal salts, they react with the soluble phosphate to form the solid precipitates, and these precipitates are removed by the separation process including the clarification and filtration. The chemical treatment is the most common method used for the removal of phosphorus to the concentration below 1 mg per liter. When lime is used, a sufficient amount of lime must be added to increase the pH of the solution to at least 10, creating an environment in which excess of the calcium ions can react with the phosphate to form the insoluble precipitate of hydroxyl apatite. Lime is an effective phosphate removal agent, but it results into the large sludge production. When ferric chloride or alum is used, the iron or the aluminium ions in the solution will react with the phosphate to produce the insoluble metal phosphates. The degree of insolubility for these compounds is dependent on the pH. Moreover, many competing chemical reactions can also take place alongside, meaning the amount of metal salt to add to the solution cannot simply be calculated on the basis of phosphate concentration, but must be determined in the laboratory for each case. Next, for the removal of suspended solids which are there in the water, the fine particles, because of their small size, they escape the filtration, sedimentation and other similar removal processes. Their small size allows them to remain suspended over extended periods of time. These suspended particles in the wastewater are negatively charged, so the cationic polymers are generally used to reduce the surface charge of these suspended particles, causing them to get coagulated and settled. Alternatively, lime can also be used as a clarifying agent for the removal of this particulate matter. The calcium hydroxide reacts in wastewater solution to form calcium carbonate, which itself acts as a coagulant, sweeping the particles out of the solution. The amount of chemicals which are required for the treatment, it depends upon the physicochemical parameters like pH, alkalinity, phosphates present in the water to be treated. And the interference of the co-contaminants actually makes it difficult to calculate the quantities of the chemicals which are needed for the precipitation process. So, the accurate dose should be determined by jar test and should be confirmed by field evaluations. Students, in this module, we had learned the coagulation-flocculation process as well as the precipitation process for the removal of suspended and dispersed particles from the wastewater. In the coagulation and flocculation process, the colloidal particles, which are the small size particles which escapes the conventional separating techniques like sedimentation, filtration and centrifugation, they are made to flock together to form the bigger particles, bigger clusters which settle down of their own as a result of the gravitational force. We had also studied that how to go for the optimization of the dosage of coagulant, the kind of the coagulant which is used and the operating conditions like the pH and the mixing rate for the maximum removal of the colloidal particles from the wastewater. Secondly, we had also studied the precipitation process and we studied the minimum solubility graphs of the metals at different pH which are needed for the removal of these metals from the wastewater. Thank you.